California, the blazing land of America's West Coast, is facing one of its most persistent and devastating enemies: drought. Rivers have run dry, and fertile farmland has cracked into red dust. And then, a bold idea emerged. Pull billions of liters of water from the Pacific Ocean deep into the mainland, build massive desalination plants, apply advanced wastewater recycling technology, and construct water pipelines stretching for hundreds of kilometers, bringing a once-dead land back to life. Are you curious about the technologies quietly powering this ambitious solution? Join Mandarin Tech as we uncover how California is battling the greatest water crisis in its history. If California were a country, its economy, worth more than 3.5 trillion USD, would rank as the world's fifth largest. And more importantly, the state's agricultural sector produces 1/3 of the United States' vegetables and 2/3 of its fruits and nuts. Yet this very agricultural giant consumes nearly 80% of all human-used water in the state. The irony is that California can hardly supply its own water. Geographically, the state sits between the cold Pacific Ocean and the towering Sierra Nevada, a natural wall that blocks much of the ocean's moisture. Most rainfall lands in the north, while the south endures a semi-desert climate. Over 60% of California's natural water supply comes from Sierra Nevada snowmelt, a massive water bank that forms each winter and gradually feeds rivers and reservoirs through summer. But that cycle is collapsing. Snowfall has dropped 20–60% in drought years and melts weeks earlier. California is now in its worst drought in 1,200 years, with major reservoirs like Shasta, Oroville, and Meade falling to just 40% capacity. That's why Americans couldn't just sit back and wait for mountain water to arrive. Instead, they turned to a nearly endless source: seawater. But seawater contains about 3.5% salt, far too salty to drink or use for irrigation. That's why desalination technology emerged, providing California with a virtually limitless supply of usable water. And to start that desalination process, giant desalination plants were built along the Pacific coast. Every day, this desalination plant converts 7 million liters of seawater into drinking water, using a significant amount of energy in just 90 minutes. The first step is to bring seawater directly from the ocean into the mainland, creating a continuous flow of raw water for the desalination plant. To do that, engineers install massive intake pipelines made from carbon steel or large-diameter HDPE, often measuring 2 to 3 meters across and built to withstand salt corrosion, water pressure, and impacts from ocean waves. Each pipe section, stretching dozens of meters, is lowered into place using heavy lift cranes, then connected piece by piece with high-pressure gaskets and fully sealed welds. Finally, the entire pipeline system is secured with steel frames and seabed anchors to keep it stable against strong currents in the harsh coastal environment. The desalination process begins by drawing seawater through pipelines that lead straight into open intake screens. The water is pulled from a few hundred meters offshore, where barriers and intake filters catch large floating debris and prevent marine life from entering. A 63-centimeter pipe can pull in up to 15 million liters per day. That's more than 10,000 liters per minute. At the intake point, powerful pumps push the seawater toward the plant. As the seawater is drawn in, some uninvited guests can show up, like jellyfish, crabs, and occasionally small fish. To keep these creatures out of the system, a massive screen is installed to block anything larger than 4.5 millimeters in diameter. After that, the water passes through finer screens to filter out the remaining large particles. Even after the larger organisms have been removed, the water is still full of suspended sediment. The solution is a process called filtration, which takes place in tanks like these. Here, the water flows downward through layers of sand using gravity. The gaps between the sand grains are so small that only water can pass through, while suspended particles get trapped. The sand continuously moves downward, opposite the direction of the water flow, and the dirty particles cling to the sand surface. After this stage, the water looks cleaner, but it still contains countless microscopic particles. Anything larger than roughly 1/10 the thickness of a human hair is removed. Next, large paddles stir the water, and the plant adds 2 chemicals: sodium hypochlorite, a disinfectant, and ferric chloride, a coagulant. The coagulant causes the fine sand and waste particles to clump together into larger flocks, which then settle at the bottom of the tank. Most of the dirt has now been removed, but the water is still far from clear enough for the desalination stage. After the water has passed through fine filtration, it enters the cartridge filtration system, the final line of defense before RO. Inside each housing are multiple cartridges made of tightly compressed fiber layers, with pore sizes as small as 1 to 5 microns. As the water flows from the outside toward the center of each cartridge, microscopic particles get trapped between the fiber layers, while the clean water passes through the cartridge wall and continues onward. Once a cartridge becomes saturated, engineers remove and replace it to ensure the system always operates at maximum efficiency. The seawater then moves to the most critical stage, separating the salt from the water. Salt is extremely difficult to remove because salt ions cling tightly to water molecules through electrostatic attraction. To break this bond, the system must apply extremely high pressure. The water enters a process called reverse osmosis, where the real magic happens. The concept is simple. Apply pressure greater than natural osmotic pressure, forcing water through an ultrafine RO membrane, while salt and other impurities are left behind. To generate this pressure, the plant uses high-powered centrifugal pumps. Each component of the pumping system controls a specific pressure stage, with the pressure gradually increasing as the water moves through successive compression phases. By the time it exits the final stage of the pump assembly, the pressure reaches about 60 bar, roughly 60 times atmospheric pressure, strong enough to separate water from salt at the molecular level. After the first round of RO filtration, the water is already almost salt-free, but it still contains trace ions and microminerals that must be completely removed to meet certain drinking water standards. So the water is sent through a second RO stage, where even finer membranes operate under lower pressure, but achieve higher salt removal efficiency. This stage reduces the water's electrical conductivity to extremely low levels, stripping out the remaining ions and bringing the water to true, purified water quality. The final result is an ultra-clean stream of water with near-perfect purity, ready for remineralization or distribution. After passing through the reverse osmosis membranes, the purified water is clean enough for irrigation, but its pH still needs to be balanced before humans can safely drink it. To do this, the plant adjusts the pH, usually by adding a small amount of acid or a balancing solution to bring the water back into a safe range. RO desalinated water also contains far fewer essential minerals than typical drinking water, so to improve taste and overall quality, a small amount of minerals like calcium and magnesium is added during the remineralization process. This step restores the water's mineral profile, adjusts the pH, increases alkalinity, and brings back a natural taste, creating water that is not only safe but also healthier and more pleasant for people to drink. The clean water is then carried through high-pressure pipelines to massive storage tanks within the plant, where it's ready to be used for irrigation or even direct drinking. From there, the water is pumped into the municipal supply network or delivered to drought-stricken agricultural regions. Although it's considered a technology of the future, desalinated water is relatively expensive, often costing 2 to 4 times more than conventional water, depending on location and operating costs. Although desalination technology is highly advanced, many people still question whether it is truly practical and suitable for real-world use. California doesn't fight drought with desalination plants alone. The state had already launched one of the most ambitious infrastructure projects in U.S. history, building a vast system of dams, reservoirs, and man-made aqueducts stretching hundreds of kilometers, powerful enough to reshape the destiny of an otherwise dry region. It all begins in the Sierra Nevada, where winter snow piles up meters deep. When summer arrives, the melting snow produces a precious flow of freshwater. Instead of letting that water rush out to sea, engineers built massive dams like Shasta, Oroville, and Folsom, creating a reservoir system with a combined capacity of tens of billions of cubic meters, water banks that protect California through every drought cycle. From there, the water is carried south through the Central Valley Project and the State Water Project. Their backbone is the California Aqueduct, a nearly 700-kilometer artificial waterway that cuts through valleys, crosses deserts, and climbs mountain ranges. In places where the terrain rises sharply, giant pumping stations push water more than 600 meters up the Tehachapi Mountains. The water is then distributed through a vast network of reinforced concrete pipelines and branching canals, reaching every city, farm, and industrial zone. But delivering each cubic meter of water to end users comes at a steep cost. Tens of billions of dollars in construction, plus billions more each year for electricity and maintenance. Many areas have had to raise prices for both household and agricultural water just to keep the system running. And now this very same water highway is opening up a new future, combining water from the mountains with water from the sea. The existing infrastructure can seamlessly connect to coastal desalination plants, allowing California to blend multiple water sources within the same network, transforming the system into the beating heart of 21st century water security. Thanks to its vast system of dams, reservoirs, and aqueducts, millions of hectares of farmland in the Central Valley, which supplies more than 1/3 of America's vegetables and 2/3 of its fruits, now have a stable, year-round source of irrigation water. Fields that once depended entirely on snowmelt can now maintain production even during severe droughts. Crop yields have increased dramatically, helping turn California into one of the most important agricultural hubs in the world. And despite the high cost of water, this system remains the backbone that allows California's agriculture to survive and thrive in an otherwise arid climate. Alongside seawater and natural freshwater sources, California has also built massive wastewater recycling plants to ensure that not a single drop goes to waste. These facilities both supply additional clean water for agriculture and cities and reduce pollution entering rivers, lakes, and the ocean. The journey of water treatment begins deep beneath the city, within a vast network of underground sewers where every drop from toilets, sinks, and even industrial facilities converges. This immense flow arrives at the treatment plant carrying an unpredictable mix: shredded paper, plastic bags, wooden branches, sand, gravel, and even grease. To prevent the entire system from clogging, the process starts with a row of stainless steel bar screens. Standing tall like the first gatekeepers, these mechanical grids trap large debris, from rigid plastics to scraps of fabric, ensuring that the flow downstream remains unobstructed. In the primary treatment stage, the wastewater that has already passed through bar screens and grit chambers is directed into enormous settling tanks. These structures, often circular or rectangular, can hold thousands of cubic meters of water and function as temporary basins, where the flow slows dramatically. As the velocity decreases, heavier organic particles, such as fecal matter, food residues, and shredded paper, begin to sink to the bottom, forming a dense layer known as primary sludge. On the surface, mechanical skimmers move continuously in circular motion, collecting floating grease and debris to leave behind a clearer middle layer of water. Through this simple but powerful mechanism, the sedimentation tank serves as the first line of defense. Once the water has passed through the primary sedimentation stage, it enters the decisive phase: biological treatment inside the aeration tanks. These are massive concrete basins, several meters deep, equipped with thousands of fine air diffusers at the bottom. Tiny bubbles rise continuously, stirring the entire water column and delivering a steady supply of oxygen. Within this oxygen-rich environment, billions of aerobic microorganisms come to life, consuming and breaking down the remaining organic compounds. In truth, these microorganisms are the invisible tiny workers, tirelessly cleaning the water day and night. As oxygen fills the tanks, the activated sludge begins to form clusters known as flocks, binding countless microscopic particles that remain suspended in the water. The water leaving the secondary settling tanks appears much clearer, yet within it remain countless microscopic particles and microorganisms, far too small for the human eye to detect. To remove them, the flow is directed into massive filtration chambers, where layers of dark membranes are arranged in sequence. This is the microfiltration system, functioning like an ultrafine gateway that blocks bacteria, parasites, and the tiniest suspended solids. The purified stream is pumped under tremendous pressure into rows of white cylindrical tubes, the reverse osmosis modules, the very heart of the entire system. Inside each tube, multiple layers of semi-permeable membranes are tightly wound, their pores hundreds of times smaller than the width of a human hair. Here, every molecule larger than H2O is stopped in its tracks. The pressure inside the system can reach tens of bars, many times greater than atmospheric pressure, driving a process that is both powerful and exquisitely precise. By the time the water exits these white cylinders, it has achieved an extraordinary level of purity, shimmering like liquid crystal. This is the decisive transformation point, where cutting-edge technology turns wastewater into water that's clean enough to drink. And that wraps up our journey with Mandarin Tech as we explored California's bold mission to reclaim every drop of water for the future. All the information in this video has been compiled from reputable sources, so if you notice anything that needs clarification or correction, feel free to share your thoughts in the comments. See you in the next video, where we'll continue uncovering the engineering marvels and technologies that are reshaping our world.